Great. So thanks for sticking around to the end of the day. The good news is that we're ahead of schedule and my slides shouldn't take 45 minutes, so we should be out of here maybe in half an hour. So I work at Nvidia. I'm a senior software engineer. And the team that I work in is called DevTech. So this is a team that in part works with external developers in order to make sure that their codes run well on GPUs. And so we were involved with the recent Blue Waters and Titan systems to make sure that the applications that were running on them ran well and scaled well. So what I'm going to be presenting here is some of the lessons that we've learned as we've worked with these applications. So as a disclaimer, this is not really work that I've done for the most part. This is work that all these brave application engineers have done. And we were just there sort of, talking with them and helping guide them maybe and definitely learning from them as they scale to large systems. The data that I'm going to be showing for the most part is on an earlier partition of Titan called Titan Dev. So before they brought online the entire machine, they had around 900 nodes available for about a year for people to start developing on. So most of my data extends only to 800 nodes because over the span of a year and a half, that's where we were seeing applications slowly improve in performance. So I keep it there, but obviously these codes are scaling to much larger numbers on Titan, much larger numbers of GPUs. So everybody here probably knows what strong scaling is. I'm going to be talking mostly about strong scaling, but the lessons we talk about also apply to weak scaling in most cases. So strong scaling is basically I keep the problem size the same, and I increase the number of processors. I expect the performance increases by the same amount. So that's ideal strong scaling. Unfortunately, in real life, sometimes we see graphs that look like this. We don't like them. We don't want to live with them. We want to make them better. And so the application that I'm going to be talking about most in my talk is called Nambe, and it's a molecular dynamics application. And basically what it's trying to do is, here's a really simplified, non-scientific way of saying it. You have atoms, and they're exerting forces on one another. You want to find out how these atoms move over time. So why is strong scaling so important for applications like this? Let's just get an idea for the time scale in which biological activity happens. Here's the time scale. We're starting at femtoseconds, ending at seconds. We have a pretty small system here. It's 92,000 atoms. So one time step of simulation, unfortunately, is limited to the femtoseconds by the Nyquist limit. And it turns out that biological activity that scientists might care about really starts happening at nanoseconds and more. So say I had a scientist and he cared about simulating a microsecond of simulation. And that's like 10 to the 9 time steps that he would need to do. If he was to use a single GPU and the code that was Nambe 2.8 about 2 years ago, that would mean he'd have to wait more than 2 years. So that's sort of sad. And if you wanted to speed this up, you could say, well, okay, let's scale it over multiple GPUs. The amount that he could have gotten an improvement is about 2x improvement. And beyond that, for this small system, Nambe stopped scaling. For larger systems, it was much better. But that meant he still had to wait almost 2 years. Almost a year. And with the improvements that the Nambe team put in over the last couple of years, now at 50 nodes, he only has to wait 20 days. So strong scaling makes science achievable, right? That 568 days is really, it's out of the realm of possibility for a grad student to wait, right? So we're making them more productive. Instead of waiting 2 years and playing World of Warcraft on your GPU, take that GPU, scale your system, be done in 20 days. And then spend the rest of the days playing World of Warcraft. So here's some of the results that I was talking about. We started with Nambe 2.8, and really it stopped scaling at about a couple of nodes for this system. So the numbers are sort of, the colors are sort of unintuitive. The blue is actually a GPU. Usually we would use green, but anyhow. So over time, we tracked the improvement of performance of scaling for this system, and I stopped tracking this last year. At that point, we had done about a 10x increase in performance at scale for the GPU code. And here's a much larger system. This is a 100 million atom system. And similarly, we got pretty good performance improvements here. Just note that the intermediate results are for what we estimated the NVIDIA Kepler GPU would be, because at that point, GPUs were actually not available at scale in either of these machines. But this number on the very right, these are actually measured numbers. So blue line is Fermi, which is our previous generation of GPUs. Green line is Kepler, which is the actual GPU that is in Titan and Blue Waters. So this was just a motivation to say you could have an application that maybe is not scaling very well on GPUs, but there's steps that you can take to improve the performance. I'm going to be talking about some of these steps. They're not that hard. It's not a lot of work. In some cases, you just need to know what the problem is. And I'm going to divide up what I'm going to be talking about into 3 parts. And I'll try to focus on things that might be specific to a GPU cluster. So I don't want to tell you how to improve the scaling of your application on a CPU code, right? You know how to do that. But if you then port your application to a GPU, what might be additional problems that you might run into? So the first is that you've written now this code that is managing the GPU. It's packaging work to the GPU. It's processing work that is coming off of the GPU. Maybe this work, this code, this function isn't scaling very well. The second part might be the most obvious to people. Oh, I have a GPU cluster, performance isn't scaling, there must be something wrong with the GPU kernels themselves. And that could be an issue, and we'll look at that. And then the third thing is, communication is a bottleneck. So what happened was, you made computation a lot faster, and then it turned out that something that was not a bottleneck before becomes a bottleneck. And most often, this might be communication. And so you have to pay more attention to communication when you're in a GPU cluster than you might when you were in a CPU cluster. So we'll start with improving the performance of the code that is managing the GPU. So there's a function that you probably have that is accumulating all the data that is coming in for the GPU function and kicking off this GPU work. So make sure that this function is scaling. In Nambe, for example, this function wasn't scaling very well, either across nodes or across cores. And improving that scaling helps performance. Another thing is, how is the application determining when the GPU is done doing the computation? So again, in Nambe, what the developers were doing was they had an event query. So they would issue their kernel, they would issue an event, and then they would query this event to find out when the kernel was complete. And if the event was not yet done, there would be a follow-up event that would be, or a follow-up to query that event after a certain amount of milliseconds. And just tightening that loop, reducing the amount of time until you query the event again, made a huge difference in performance. So here, we reduced the amount of time to query events, and it's almost a 10% improvement at 16 nodes, but it's a 52% improvement at 50 nodes. So that really improved scaling. Another point, is your application using MPI? And if it's using MPI, is it the case that each MPI rank is sending work to the GPU? This might be a very natural way for people to program, right? You had your work divided up amongst all the cores, and each core had an MPI rank on it. And now you just accelerate some portion of the work, and to do that, each rank takes that portion of the work and kicks off a GPU kernel. The problem is that each MPI rank has a separate GPU context. And kernels from different contexts don't run on the machine at the same time. So I'll give an example of why this is such a bad thing and why it's an even worse thing at scale. But just as a preamble, you don't need to do this. So there's ways around running into this issue. So the first obvious one is don't use an MPI rank per core. Instead, you can use threads, and all the threads would share a context, and so you wouldn't have this issue. All the kernels from the context would run at the same time on the GPU. Another thing, if you are using a system like Titan or Blue Waters, you can use a CUDA proxy server. So basically, proxy allows an application to use multiple contexts and still run concurrently on the GPU. So all of the kernels from different contexts, if they're using proxy, run on the GPU at the same time. And then finally, here's an example of what we did in Nambe's case to start off with. And that was all of the multiple MPI ranks would not submit work to the GPU. Instead, all of them would submit work to one master MPI rank, and that MPI rank would then kick off the work. So I'll just show an example of how that helps performance. So here's what we were talking about. There is a couple of cores on your node, and you map an MPI rank per core. And now these MPI ranks say, oh, look, there is a GPU. I'm going to kick off some work to it. And so each of them kicks off work to the GPU. Each of them has a separate kernel. And what ends up happening on the GPU side is the kernels get serialized. So first, the first kernel runs, then you have a fixed context switch overhead to switch to the next context, and then the second kernel runs. And so the reason why this is bad for scaling, there's two reasons. As you start scaling your work, the kernels become smaller and smaller. And that context switch overhead, the thing in the red in the middle, that doesn't change. And so it becomes a bigger and bigger portion of the runtime. Even worse though, as you make your kernels smaller and smaller, they are using the GPU less efficiently because the GPU is a throughput architecture. So what you really want to do is run both of the kernels at the same time on the GPU. And you could get as much as a 2x improvement in performance if both of those kernels could run at the same time because they were small enough. So instead what you can do, have your two MPI ranks, one of them communicates the data to the other rank, that rank launches the kernel, there is only one kernel, and the application is done sooner. So this actually gave a really big performance advantage. So here, just over 16 nodes, the GPU was losing to the CPU at a couple of nodes when we started off. So here's like the flatline GPU performance at the bottom of the view. And just by making this change, we get the graph on the top, the green one. So the second part is, what if the GPU kernel itself isn't scaling? So the first thing to look at is, your GPU kernel isn't scaling. Can you make sure that the work to the kernel is scaling? So for example, if you are now using twice as many GPUs, is each of the GPUs getting exactly half as much work? If it's not, then you have a load imbalance, and that might be creating scaling problems. So can you load balance work better across GPUs? And here's a really obvious example. Amber is another molecular dynamics application, and the issue with Amber is, so here's a tau plot. I don't know if any of you have used tau. It's a performance analysis tool, I suppose. So what this is showing is, I've got two cores, and each of them has a GPU on it. And there's functions that scale. So there's like this yellow part that is on both, that is being run on both GPUs. But then there's these green functions that are only being run on one GPU. So obviously, as you scale to larger and larger number of GPUs, but you're keeping some part on just one GPU, obviously things don't scale very well. And when we look at the performance, we see that at 8 nodes versus 2 nodes, their performance increase is only 1.7x. And we would have liked it 4x here. That's perfect scaling. And if you use Amdahl's law and you factor in what is the cost of this part, at most they could have gotten a 2.1. So the fact that they're limiting some amount of work to only one GPU limits the performance to at most 2x versus 4x. So try to load balance work better across all of your GPUs. The second is launch latency. So as you scale the amount of work to the GPU, the kernel might scale. But there is some fixed cost that doesn't scale. And part of this cost is launch latency. So it's the latency of launching work to the GPU. So here's the most obvious example. I have a CPU, it launches a GPU kernel, the GPU kernel does some work, and then the CPU forces a synchronization with the GPU. And let's assume that our GPU kernel actually isn't doing anything. So in that case, the launch is 11 microseconds. And if we weren't doing a synchronization with the CPU, things are a little better. So it depends what sort of streams you're using, but we get just 4 microseconds. But this is something to keep in mind. If your kernels are running for such a short amount of time that this is a significant fraction, which we actually don't see that often, but for strong scaling, this could become an issue, right? Then this is a big part. This might be a big part of your runtime, and then this is the thing that is causing scaling problems. And launch latency can become worse. So this is launching an empty GPU kernel. But if you start binding textures, for example, so textures are one way of accessing data in a very random fashion. If you were accessing using textures and you were using this legacy API that binds textures, so you can bind a texture explicitly to a kernel, every time you bind a texture, that is a fixed overhead of 0.5 microseconds to the launch overhead. And that can stop your scaling. So here I have an example of lattice QCD. So this is the code that tries to probe what is happening inside a nucleus. And we saw that we were sort of tapering off in scaling because of these launch latency issues. But in this case, the problem was they were binding all these textures. So with Kepler and CUDA 5, which are both out publicly now, you can instead use binders textures, and those reduce the launch latency. So try to reduce this fixed overhead. And when we reduce the fixed overhead, we see much better scaling. So the next part, maybe the work to your kernel is scaling, but the work is not enough to fully saturate the GPU. So like I said, it's a throughput architecture. At some point, you might be running too few threads to utilize the GPU properly. If that's the case, there's a number of things you can try doing. For example, maybe your threads, there's not enough threads, and each thread is doing too much work. You can try chopping down the threads, make them smaller, and run many more of them, and that way you're filling the machine better and being more performant. Or you can run kernels concurrently. So if each of your kernels, your GPU kernel, doesn't take that much time and is not utilizing the machine very well, try running many of them at the same time, which we allow since Fermi. And with HyperQ, which is a Kepler feature, it's very easy to have multiple kernels running at the same time. And then finally, there's something called the tail effect. So I apologize in advance, these slides are a little confusing, so pay attention now. So say, for example, you're scaling work to each GPU perfectly. Say that there is more than enough work to saturate the GPU. You could still run into issues if you haven't load balanced the work very well within the block. So within all the little chunks of work that are running on the GPU, it could be the case that some of those chunks of work run for a lot longer than other chunks of work. So let's see why that would be an issue for scaling. So here, for example, I have a number of little chunks of work that are running on the GPU. So we start off with these 4 chunks, they're done, next 4 chunks, next 4 chunks, and they run for a certain amount of time on one GPU. If I want to scale this to 2 GPUs, I divide up the work in half, and it turns out that each GPU will now take exactly half as much time, perfect scaling. Now say, for example, I've got another set of work. It runs for the same amount of time on one GPU, but it's got this really bad load balancing. Some chunks of work run for a lot longer, others for a lot shorter. Now if I try dividing up this work over 2 GPUs, it turns out my runtime hasn't divided in half, right? So GPU 0, instead of taking just this much amount of time, takes this much amount of time, because there's this one little straggler that runs for a lot longer. Same with GPU 1. This GPU 1 basically is running for this one little chunk of work. All the rest of its work is finished. And so your scaling gets worse and worse. The less work you have and the more imbalance you have between the work. So this is what we had observed in Nambe when we were trying to scale to large amounts of nodes for this very small problem. Our parallel efficiency for the GPU kernel itself, not that big. So the hypothesis was that we're running into this tail effect where you have load imbalance between the blocks of work, and some little blocks of work are holding up completion. So in order to figure that out, or in order to prove that hypothesis, we did a little measurement of all the kernels running on the GPU. So here we are basically showing for each of the blocks running on the GPU when that block starts and when that block finishes. So all this diagram is trying to show is there's lots of blocks that take a relatively short amount of time. There's some blocks that run for a really long time. And these guys, they're the ones holding up the GPU, causing scaling inefficiency. So for the last quarter of the runtime of the entire kernel, these are what, I don't even know how many blocks these are, but these are like in the thousands, many thousands of blocks. But quarter of the runtime is basically like these 5 blocks. So you can see why this is a problem for scaling. And we built a little model to say, if we were to improve this load balancing, if we were to get perfect load balancing, we could get a 52% improvement in the runtime at 32 nodes, and we would get almost perfect scaling of the kernel at that point. So load balancing, the blocks of work on the GPU makes a difference. It doesn't matter to the CPU, right? You have a loop, you're going through chunks of work, one chunk of work takes a very short amount of time, the next chunk of work takes a very long time. What does the CPU care? The GPU cares, because it's running all in parallel. So the third and most important part, the GPU has nothing to do with it. Your GPU code isn't scaling on GPU clusters, and it turns out is the problem with the communication. So there's a number of things you can do, and this applies equally well to codes that don't even run on GPU clusters. So the first thing that the developers tried doing was try changing the messaging. So it turned out on Cray clusters, MPI was not performing that well. And changing to this native UGNI messaging, so more low-level messaging, started improving performance like at 4 nodes. So the performance improvement for GPU scaling actually kicked in even before the performance improvement for CPU scaling. Because the GPU is so much faster, communication is more of an issue. So here's a number of just common sense things that people would do if you were communication limited. Reduce congestion by doing throttling and by doing rendezvous messaging. So, have your sender send a little control message, and then the receiver can initiate the get. Reduce global syncs. So Amber, this application that I showed, has a lot of global syncs. So instead, try doing one-sided operations whenever you can. Here's an actual example that we have from a code called QMC Pack, which is doing quantum Monte Carlo. So it's modeling quantum systems. And this is a weak scaling problem. So just as a disclaimer, this looks like it's bad scaling, but it's actually better than 90% efficiency because the y-axis starts at 600. So this is really false advertising that, it's a lot better than it looks. So the line should be flat, would be perfect weak scaling. The red line is where it was, and then the blue line is with an improvement, which is that they started doing asynchronous MPI messages to all the nodes. So instead of having one message go out and then the next and then the next, they sort of parallelized this. And that helped improve the overall performance. Here's another example, also from QMC Pack. They had some inefficiency in just their communication path. So this is the original. And then they removed some of these pinned memory allocations. So they were pinning memory inside the path that was copying data to the GPU, copying data back off the GPU, and sending it across the network. And they were pinning that memory in hopes of making the transfer faster. But the pinning itself is an expensive operation. And so just removing that from the MPI communication path led to an improvement in performance. And then topology is a factor. It could be the case that you have an inefficient network topology for the application that you care about. And we've seen sometimes that we're comparing, for example, the performance of a GPU cluster against a CPU cluster, but the CPU cluster has a much better topology. So just try to ensure that topology isn't a factor. And if you're really, really brave, you can try topology-aware node mapping. Overlap. This is something that Dikipanda brought up earlier, which was try to overlap the memory copies that you're doing with the communication that you're doing. So memory copies that you're doing off of the GPU, for example, with MPI communication that you're doing across the network. So don't do a synchronous mem copy and then do a synchronous MPI. And it's already built into his code, so you don't even need to worry about it. Another thing, if your CPU core is responsible for both the maintaining the GPU kernel and also for the network polling or just basically getting network data off of the network, CUDA synchronized or synchronous copies are again an issue. So here are two examples. Say I issue a kernel and then I issue right afterwards a CUDA synchronized. What that means is your core is blocked from doing anything else until the kernel returns and your synchronized completes. So if you do this, you launch your kernel, you issue a CUDA synchronize, and then when the kernel is done, you then go back to the network and start polling it for messages. This is a slow path. Similarly, if you issued a kernel and right after the kernel you issued a synchronous mem copy to copy data back off of the GPU onto the core, that's another slow path because now you have to wait for this to complete. Your core is sitting here idle, not doing anything, and then when it's done, then it starts polling the network. So, wrong approach. Here's the right approach. Launch the kernel and then start doing your network. If you have to do anything with the network, start doing it here. And once in a while, you can check for events. So check if, check that the kernel is complete. No, not complete, go back to your network. And when you're done with the network, if you have nothing else to do, feel free to sit there and wait for the kernel to complete. And same here, poll the network and then issue an asynchronous mem copy instead of a synchronous mem copy. And that way you've overlapped your network with your GPU work. And then finally, never underestimate the change that you can get by just changing your algorithm. So for Nambe, the Nambe developers tried a number of these strategies. They tried throttling and they tried rendezvous messaging. And all of those things sort of helped. But the biggest thing that helped was changing the algorithm. So here's the performance that we were running into. This is with Fermi, so our last generation of GPUs. This red line is what we were measuring before, so not very ideal scaling. The little dotted red line, that's what we would like to see. That's ideal scaling. And then with the algorithmic changes that we're going to discuss, we got much better scaling, so that's the green line over here. So when we were trying to figure out what was the problem with this bad scaling, we looked at profiles of the code. And so here we have data for 32 nodes, and then again for 768 nodes. And we see how each of these sections of the code are doing. So here's the total time step. It wasn't scaling very well. The GPU kernel itself, it was scaling almost perfectly. So we're like, don't bother with the GPU kernel at this point. So molecular dynamics has two steps, a PME step and a non-PME step. We won't go into what those mean, but non-PME was doing great, PME step was doing horrible. So that was an indication of let's go find out what's going on with this one. And so here's an image from this really awesome tool that Nambe has built inside, and it's actually part of Charm++, which is what Sanjay is going to be talking about tomorrow. And this tool really helped us visualize a lot more of what was going on than even we could have seen in any of the other tools like Vampire or any other tool that you could think of. So it's really a great tool. And what we saw was, at 32 nodes, there was a little bit of idle time. There's a little bits of these little chunks of void. At 768 nodes, there were these huge amounts of idle time. And so it turns out that these huge amounts of idle time are the reason that we're getting such poor scaling. And these were because messages were getting delayed. And the best thing that we could do to fix these large amounts of idle time was just change the algorithm. So instead of having a lot of communication, change the algorithm so that you reduce the amount of communication and have more sophisticated computation. So it's more expensive, the computation. Doesn't matter because communication was the bottleneck. And overall, you get this really nice increase in performance. So here's Fermi before, 1.2, and then it became 1.5. And then Kepler, which was also around 1.2, and it became 1.8 nanoseconds per day. So here's the conclusion. We've discussed a number of ways that you can improve the performance of code that is scaling on clusters of GPUs. It's important to first figure out what is the problem, what is limiting your performance. And the answer is not always the GPU. So try to make sure that you understand what is the problem. And then a lot of these changes, they were really modest. So you don't necessarily have to put in a large amount of work in order to get a really good benefit to the scaling of your application. And now with Blue Waters and Titan, you have really large systems of GPUs, clusters of GPUs that you can use. So it's great if you can improve the scaling performance of your code on GPUs and take advantage of these large systems. So that's all I have, and I'll take questions.